Yes. So thank you. This paper is joint work with Ingo, Tim, and Klaus, who are not here. So the first question that you might ask yourself is, what could this paper possibly be about? And in order to answer that question, I want to tell you what my working definition of object-oriented programming is. And my definition that I'm going to use is that object-oriented programming consists of three parts. There are co-data types, which correspond to a purely type-theoretic description of interfaces, programming against interfaces. There is subtyping, and then there's open recursion or late binding. But in this talk and in the paper, we will concentrate on the first aspect, which is strongly related to the extensibility and modularity properties which distinguish functional programming from object-oriented programming. So if you're interested in this, there is prior work by William Cook on the problem of data abstraction. In order to show you what I mean with the difference between functional programming and object-oriented programming and how they differ in their extensibility properties, I'm going to start with the simplest possible example, the example of Booleans. So in functional programming, we would define the Booleans as an algebraic data type defined by two constructors, true and false. And we can program with this data type, here, for example, by implementing the negation function by pattern matching on this. So here we have defined bool as a data type and negation by pattern matching on the possible constructors. If we would define this in an object-oriented style, then we would define Booleans not by its possible constructors, but as an interface on methods that I have to implement for Booleans. Here in this example, I just consider negation, so every Boolean has to implement the negation function. And this is a form of co-data types, which are defined by the interfaces, and true and false are defined by co-pattern matching, which basically just means that every inhabitant of a co-data type must implement the corresponding interface. So we've seen that there are data types which correspond to the style of programming that you're used to in functional programming, and co-data types which correspond to programming against interfaces in an object-oriented style. And we can relate those two worlds of data and co-data types with global program transformations. Refunctionalization is a transformation which takes any data type in a program and translates it into a co-data type. And defunctionalization is a program transformation which takes a co-data type and transforms it into a data type. You might have heard of these two transformations applied to functions, but functions are just one special instance of a co-data type. And in this work, we use def and refunctionalization not as a compiler technique, but as a principled mechanism to derive a two symmetric language fragments of data and co-data types within the same language. And this can be used as such a principled mechanism, because only in languages where data and co-data types are completely symmetrical can you define those transformations in a total and type-preserving way. So these are the two representations that we have seen, and they can be related by an automatic transformation, because behind those two representations is a third one, which represents the program as a matrix. So Booleans have two ways to construct them, true and false, and an observation which observes them. And to show you that this also works in practice, we have implemented a system where you can just de- or refunctionalize any type by the click of a button using the language server protocol. But the second part of the title of our paper mentions dependent types. So let us look at the same example, but now extended to dependent types. Here we have a type of Booleans in the functional programming version. So we have two constructors, but now we have added the Martin-Löf equality type. And instead of just implementing negation, we also prove that negation is involutive. So this is a proof that applied to any Boolean here called self proves that if we apply negation twice to self, then that is equal to what we have started with. If we refunctionalize this program, and here we just refunctionalize the bool data type, then we have defined Booleans as a co-data type with the negation method and an additional proof that every object which implements this interface also has to come with a certificate that the implementation of negation is true. Yes, so every object comes with its correctness proofs. And we can also do this transformation automatically and transform any program. And I also said that this comes with applications to the expression problem. This is the original motivation of the paper. We wanted to contribute to the expression problem for proofs. So here you would have an ordinary data type representation for the simply typed lambda calculus. Here with a de Bruijn representation. This is why we use natural numbers. And you would prove properties such as type soundness by induction on this data type of expressions. But the expression problem says that it is difficult to extend these proofs with new expression nodes. For example, if you wanted to add pairs to this language. Here you can see the refunctionalized version. Don't try to look too closely, but basically an expression is defined by all the methods that we have proven by recursion, respectively induction, on the original data type. So expressions are basically an interface for all theorems that must hold for expressions. And this also works in practice. So here you can see that this is a complete proof of type soundness for the simply typed lambda calculus. And the proof is like 500 lines long. And you can transform the entire proof by the click of a button. So to give you some more examples, which show that these kind of symmetric data and co-data types are really essential. One of the properties of our system is that we do not have any built-in types. So all types in our system are defined by the user, and this includes the type of functions and dependent functions. So in the first part, you see the definition of non-dependent functions. Non-dependent functions is defined just by the application method. So what can you do with a function? You can apply it to an argument and get an element of the return type. And just to make it readable, we provide some syntactic sugar for fun AB. And in the second example, you can see the definition of dependent functions. So the p-type here has a base type A and is indexed by a type family, which is a non-dependent function from A to type, the type universe. And dependent functions are also defined by dependent function application, here called dup. And this is not a new idea that functions don't have to be built into the system. It's actually quite old. And I find this article by Anton Setzer about Java as like the primordial functional programming language quite inspiring. Another example are positive and negative pairs. So there are two ways to define a tuple of two elements. Here on the left, we have the data type representation that you can find in functional programming languages like Haskell or other languages with algebraic data types like Rust. And the first and second projection are here defined by pattern matching on the pair constructor and returning the respective element. And if you look at linear logic and substructural systems, then this way of defining pairs corresponds to the tensor, whereas the negative way of defining pairs, which is a pair is everything which implements a first and a second method, is defined by the two projections and corresponds precisely to the with type in linear logic. These two different ways of defining pairs can also be generalized to dependent pairs, or sigma types, which look a little bit more scary. But to the left here, we have the positive dependent function type, also called the weak sigma type, where the sigma type is defined by a pairing constructor, but the second element depends on the value for the first element. And here is the negative definition of sigma types, also called strong sigma types, where the sigma type is defined by two projections. And so interestingly, the first projection in that line just tells you that you can apply first projection to get the first element, but the second projection mentions the first projection in its return type. And these two representations are not like chosen arbitrarily, but if you define the program on the left and refunctionalize it, you obtain exactly the program to the right. So these two representations are linked by the end refunctionalization. So now I want to tell you a little bit about what we actually have achieved in our paper. So we present a dependent type theory with no built-in types. Every type is defined, including non-dependent and dependent function types, which is not the case for most published type systems for dependent types. In order to type constructors, for example, you usually presuppose the existence of the dependent function type or the p-type. We have a proof of type soundness, which didn't fit in the published version, but there is additional material in the appendices and an extended version on archive, where you can find the full type soundness proof. We show that de- and refunctionalization are total transformations which are total and type preserving. We can de- and refunctionalize types that occur in indices of type constructors and which are normalized and compared during type checking. And we have various examples, such as strong versus weak sigma types, various different co-data encodings of natural numbers, so not just the church encodings, but also, for example, the encodings by foo and stump, which also satisfy an induction principle. And we have some examples from for dependently typed programming. So this is what we have achieved, but I also want to talk about the things that we have not yet achieved in the paper. The most important aspect is that the system is sound, but it's not consistent. And by that, we mean that every type is inhabited by some potentially non-terminating computation. There are three reasons for this. Firstly, we use the type and type axiom. We don't check for strict positivity of recursive occurrences when we define a data or co-data type. And we don't check for termination or productivity. Then we cannot have arbitrary eta equalities, because these eta equalities will not be preserved during de- and refunctionalization. And we have some additional restrictions on the judgmental equalities that we can use during type checking. So the essential idea here is we could, of course, just adapt any of the existing restrictions from proof assistants such as ACTA, COC, or lean to make the system consistent, but that is not what we're interested in. Most of these restrictions will not be preserved under de- and refunctionalization. So if we start with a consistent program and de- and refunctionalize it, then we will end up in some cases, or in interesting cases, where those ordinary checks are no longer fulfilled. So lastly, we have an implementation. This is where you can find kind of the immutable version that we provided for the artifact submission, which will not change. It is implemented in Rust. We have an LSP server and VS Code extension. But all the examples are also compiled to WebAssembly and run in the browser. So you can try out all those examples yourself. And for example, one of the interesting ones is the proof of soundness for the simply typed lambda calculus. You can take any of the types and just look what happens if you de- or refunctionalize the type. And we're still actively hacking on this. And since I know that this talk is going to be published on YouTube, I'm going to end with the obligatory. You can like and subscribe us on this site where you can follow the development. Yes. And now I'm happy to take any questions.
Thanks for the talk. Really cool work.
It doesn't work. Do you support quotient types in your system?
Sorry?
Do you support quotient types in your system?
That's a very good question. So you mean quotient types in the sense of like homotopy type theory? And yes. This is, I don't know whether we discuss it in the future work section, but this is one of the avenues to maybe add back more of the judgmental equalities and eta equalities which are currently lacking. So the problem is that if you have two different terms which might be eta equal, they get defunctionalized to different constructors. And two different constructors of a data type are no longer judgmentally equal. And so we have been thinking about adding something like quotient types to have like a data type with two different constructors standing for two different functions with an, where we quotient out by the original eta equalities valid in the program. Yes.
Okay, thank you very much. Amazing talk.
All right, so thank you. And I was curious regarding when you have these kinds of dualities, right? So you have positive, negative, you have the functionalized, defunctionalized. Oftentimes, one of the properties of essentially some proofs are easier in one side, other proofs are easier on the other side. So, could you tell us maybe quickly what are the easy proofs on one side, what are hard on the other side, vice versa?
If we actually use the system, or
sure, you prove some properties in this system, right?
I don't know if I can give a good answer about whether it is easier to prove something. One of the original motivations was really about extending proofs, so about like proof engineering and proofs over time.
Right.
And there we are interested in what does it mean to have a proof for an existing language and to extend this language with new features. And there we think that using codata types, which are extensible in the direction of new producers, makes it easier to extend existing proofs.
Anything in the other direction, like easier on the functional side?
I don't have like a good example that I can give to you right now, but
thank you.
Yeah, I can think of one.
Yeah,
Thanks.
We have time for one more quick question.
Right, so what I was wondering about is what happens if you keep defunctionalizing and refunctionalizing.
Mm-hmm.
Does this converge somehow, or may it diverge, or?
Yes, so one, if you don't use local pattern matches and only top-level pattern matches, then the two transformations are inverses, modulo alpha equivalents, so the variables are being renamed. If you use local pattern matches, then you would have to inline them again in order to obtain the original program. But yes, basically it's stable, so you can defunctionize and refunctionalize, and they are inverse of each other.
Thanks.